On February 3, 2020, the Diamond Princess cruise ship was quarantined in Yokohama, Japan, after a passenger tested positive for COVID-19. The neighboring tri-cities of Tokyo, Yokohama, and Kawasaki together have a population of about 16 million. A few days after the ship docks, based on the projected spread of the virus, it is estimated that about 1,000 people out of the 16 million are infected. At that time you are in Tokyo. Although it did not happen in reality, let's say the cities ordered mandatory COVID-19 tests for everyone. The test has a 99.9% accuracy, meaning that if you are infected, the test will be positive 99.9% of the time, and if you are not infected, the test will be negative 99.9% of the time. Your test shows a positive result. What is the probability that you have COVID-19? Is it A, 99.9%? B, is it higher than 50%? C, is it higher than 25%? D, is it lower than 10%? Please pause and think before you continue. If the only information we had was that no more than 1,000 people out of 16 million were infected, then the probability that you have COVID-19 would be 1,000 divided by 16 million is equal to 0.00625 equals 0.625%. Likewise, if the only information we had was that the test was 99.9% accurate, then the probability that you have COVID-19 would be 99.9%. But we have both pieces of information. We know that no more than 1,000 people out of 16 million were infected, and we know that the test is 99.9% accurate. Let's see how to combine these two pieces of information. First, let's look at the set of infected people. It has two parts. Of the 1,000 infected, 99.9% or 999 of them are expected to test positive, because the test has 99.9% accuracy. And the remaining one of the 1,000 infected people is expected to test negative. But that's not the only set of people we have to consider. Of the remaining 15,999,000 uninfected, 0.1% of them will test positive. That is 15,999,000 times 0.1 divided by 100 is equal to 15,999 of the population will test positive even though they are not infected. And, of remaining 15,999,000 uninfected, 99.9% of them will test negative. So 15,999,000 times 99.9 divided by 100 or about 15.98 million uninfected people will test negative. When you tested positive, you are not in the set of people in either the blue or green rectangles who tested negative. So let's remove them from consideration. You may be one of the people in the red or purple rectangles. The red rectangle has more than 15 times the number of people as the purple one, so your chances of being one of the people in that group are much higher. Probability you tested positive but don't have COVID is number of people in red rectangle divided by number of people in red and purple rectangles equals 15,999 divided by 15,999 plus 999 equals 94.1%. The high 94.1% chance of not having COVID is because the red rectangle, with 0.1% of 15.999 million, has more than 15,000 uninfected people falsely testing positive. In comparison, the purple rectangle has only 999 infected people who test positive. The probability that you have COVID-19 is 999 divided by 16, 998 equals 5.9%, much smaller than 99.9 accuracy. The reason it's small is that only 1,000 out of 16 million people infected, the 999 true positives are small compared to the more than 15,000 false positives. What we learned above is conditional probability of an event given another event, in this case probability of having COVID given that only 1,000 people are infected and 99.9% test accuracy. And we touched on Bayes' theorem without knowing it. We will do this in more detail next. Bayes' theorem equates approaching the intersection of two sets in two ways. Start with the set of people who are infected, blue and purple rectangles together, and go to the subset that intersects with people that test positive. Or start with the set of people who test positive, the red and purple rectangles, and go to intersection with the people who are infected. In both cases, we get to the purple rectangle. The first set, of infected people, is the union of the set of people who are infected and will test positive and the set of people who are infected and will test negative. The second set is the set of people who will test positive. This is the union of the set of people who are infected and will test positive, the purple rectangle, and the set of people who are not infected and will test positive, the red rectangle. The intersection of the two sets is the set of people who are infected and will test positive. This is the purple rectangle. Let's approach the intersection, the purple rectangle, in two ways. First, from the first set. First, let's find the probability of you being in the set of infected people, the blue and purple rectangles, and then multiply it by the probability of being in the smaller subset who test positive, purple rectangle, given that you are in the bigger set. Or probability, intersection of sets, equals probability, infected, times probability, positive given infected. Another estimate is the probability of belonging to set of people who test positive, the red and purple rectangles, and multiply it by the probability of being in the smaller subset of infected people, purple rectangle, given that you already belong to the set that tests positive. Or probability, intersection of sets, equals probability, positive, times probability, infected given positive. The two ways of estimating the probability of being in the intersection of the two sets are equivalent. This is Bayes' theorem. The right-hand side is probability, infected, times probability, positive given infected. The left-hand side is probability, positive, times probability, infected given positive. They are the same, and the only thing we don't know is probability, infected given our positive result. Using the equivalence, probability, infected given positive, is probability, infected, times probability, positive given infected, divided by probability, positive. Instead of set of infected if we use set B, and instead of set of positive if we use set A, then we get the common way of stating Bayes' theorem. Probability of being in the intersection of the two sets is P, B, times P, A, given B. It is also the same as P, A, times P, B given A. Now let's finish the problem by computing the remaining quantities of interest. The probability of being infected is the probability of being in the blue and purple rectangles. This is the number of people who are infected divided by the total number of people and equals 1,000 divided by 16 million. The probability of being in the purple rectangle, given you are infected, is 99.9%, the accuracy of the test. We multiply the two probabilities we just computed to get the probability of being in the intersection, the purple rectangle, and that equals 999 divided by 16 million. The probability of being in the set of people who test positive, the purple and red rectangles, is the 999 infected who test positive plus 16 million minus 1,000 times 0.1% who will falsely test positive, divided by 16 million. Using the last three probabilities in the fourth equation, in pink, we get the probability of being infected given that we tested positive as 999 divided by 999 plus 15999, or 5.9%. This is much lower than the 99.9% accuracy of the test. Key learning. 1. Conditional probability is the odds of an event happening given another event. Example, odds of being infected given a positive test result. 2. When we are trying to compute the probability of an event given two distinct pieces of information, example, test accuracy is 1, and number of infected people is another, we have to look at the intersection of the two events. 3. Bayes' theorem gives a way of computing conditional probability. It computes the probability of the intersection of those two events in two different ways. P, A, times P, B given A, and sets it equal to P, B, times P, A, given B. 4. This equality allows us to compute P, A, given B, by setting it equal to P, A, times P, B given A, divided by P, B. 5. For our example P, A, odds of belonging to infected group 1016 million is smaller than P, B, the odds of belonging to the false positive group. Hence, the high P, positive given infection, did not lead to a high P, infected given positive.